A very good evening, everyone. Welcome to this Royal Aeronautical Society Heathrow Branch webinar. My name is William Lee. I'm the Honorary Secretary of the branch and the moderator for today's session. Joining me today is Giuseppe, as well as Branch Chairman Peter, who will be hosting today's webinar. Before I hand over to Peter, there are a few housekeeping points that I would like to clear out the way. First of all, please feel free to share your thoughts about today's event on social media channels such as LinkedIn or Twitter, and to interact with us. Secondly, if you are required CPD certificate of attendance for your own initial or continuing professional development records, please use the Q&A panel now to inform us your names, and we will email this to you post-event. Your microphone is on mute, but throughout the webinar, we encourage you to use the Q&A panel to raise any questions that you may have, and you can also interact with us by clicking the thumbs up or like button next to each questions that are being published. Finally, I would like to make you aware that today's session is being recorded and will be made available via our podcast and YouTube channel post-event. So without further ado, let me hand over the foreplay to Peter.
Thank you, William, for the welcome and the high-level introduction to today's event. Hello, I'm Pete Fryer, the Chair of the London Heathrow Branch of the Royal Aeronautical Society. I'm exceptionally pleased to be able to personally welcome all of our viewers, our Society members, branch members and guests of the branch personally to the London Heathrow branch. After last month's successful return to a face-to-face lecture format at Waterside, our first since the enforced shutdown of the COVID pandemic, this evening we're returning to the format of a live lecture delivered by webinar. Tonight, our lecturer Giuseppe Calabrese has been secured for us by our committee member Hania Mahoudin. We are very pleased to present a lecture on an astronautics theme entitled Design Principles and Considerations from Earth for Space Structures on Mars, which will investigate future settlements on the surface of the great red planet Mars. Giuseppe is an award-winning architect based in Italy and registered as a member of the Australian Institute of Architects, practicing his trade in both Italy and Australia. He has accumulated a breadth of experience across different scales and complexities of architectural projects in the design of documentation of small to large scale architecture, including high-rise buildings, visitor centres, museums, hotels, heritage extensions, boarding houses, schools, offices, public spaces and renovations. He is passionate for architecture in the extreme environments with a meditative mind that draws inspiration from natural and biological forms and processes. This has led him to become a space architect with interests in physics, anti-gravity and permaculture, building a career on topics of interplanetary architectural and spatial solutions for hostile environments. He is currently a PhD researcher in the International Research School of Planetary Sciences at the G.d'Annunzio University in Pescara on the Italian coast. He is head architect at CAG in Australia. He has been a guest speaker at several conferences on terrestrial construction and a contributor to magazines and books worldwide on the subject while actively continuing his research. A published author of scientific contributions on Earth architecture, heritage and restoration, and moon research. Giuseppe is a member of the Moon European Consortium, the Mars City Design Ambassador 2022, and is a full scholarship winner of the International Space University, sponsored by the Agenzia Spaziale Italiana, using his wealth of experience in the design of terrestrial buildings and their restoration. In the presentation, Giuseppe will link together research on earthly architecture with space architecture, encompassing in situ resource utilisation on Earth and the possibility of its use on Mars. He will illustrate the definitions of extreme environment, the Mars checklist and resources, construction elements, criteria for Martian outposts, health considerations, the greenhouse for Mars, presentation of the award-winning SPOUT project for Mars, and the need for further research, not only for a future space output, but to directly benefit planet Earth. To all of our audience, today, if you have any questions for Giuseppe, I encourage you to pose them through the Q&A window, which can be opened from the question mark button After the lecture, I will pose these to Giuseppe. I will pass you over to Giuseppe, who will present his lecture, Design Principles and Considerations for Earth and for Surface Structures on Mars. Buonasera, Giuseppe, come esta? A very warm welcome to the Royal Aeronautical Society's London Heathrow branch. The stage is all yours.
Thanks so much. Thanks so much, Peter and William, for the presentation. That was fantastic. I would always also wanted to thank Hanya, my student, for making first contact, and I really appreciate the invite. It's an honor being here. I hope the whole audience will enjoy this. All right, so today we're going to talk about design principles and considerations from Earth for surface structures on Mars, as Peter and William said. So my name is Giuseppe Calabrese. I'm an architect. At the moment, I'm doing my PhD at International Research School of Earth and Planetary Sciences in Pescara in Italy. I am basically studying ISRU, so in situ resources, and with a concentration basically for habitats. So for habitats for the Moon and the Mars. That's my aim on studying materials and finding something novel, some new solutions. I'm passionate for structures in very difficult environments, and I've done a number of competitions in this sort of setting because I love the challenges. I'm also working in Sydney as an architect in the meantime, and I've been just recently returned from Australia after 18 years. So at the moment I'm located in Italy. Okay, so I'm going to do a little bit of a travel through starting with Earth buildings. So Earth buildings, we're talking about buildings that are on Earth, yes, but they're made out of, they're usually called mud buildings in a disparaging way, but they are buildings, there's a third of the population of the world that are actually living in these buildings. They're made out of earth. They are bricks made out of mud, clay. In Italy, there are many of them. I did my master's in heritage and restoration, and instead of choosing, well, I chose a couple of churches to restore. That's what you typically do, but it was the first time I chose a building made out of these mud bricks, which is very uncommon and not known to the general public. They're very hard to also spot because I had a little moped and go around in the countryside trying to find these and locate them. They are the same color of the earth, so you would never see them. So you really need a motorbike to go in the fields and try to locate these little buildings that they're beautiful. So you can see on the top left, the olive tree is, you can see this is a two-story building made out of blocks, and the wall, you can see in the bottom left here, made out of bricks, and some of these bricks are also put on a herringbone pattern. We later found that also the cupola in Florence by Brunelleschi has these herringbone shaped bricks put in this herringbone shape for possibly for static reason, earthquake resistance. And the different types of clays that are used are generally collected from a well. That's the top right image. So the well was excavated, of course, for water, but also you would find at different depths, different types of clays. So there was a certain type of clay that then will be put on the buildings as a sacrificial layer, because of course it will get weathered down, and you would be replacing that over time. So the different types of clays get used for different types of occasions. The bottom image is me, and these. So going around in the countryside, I found many of these, and I started to map them. So on the top, you can see there's a complex of buildings behind these buildings, and the collapse. The left-hand side, you can see a little oven there. That's where they bake the bread and you know, cook generally. So that's the cooked part with bricks and rocks. The bottom left, I found also these types of little sheds which were made out of fired bricks and mortar. The mortar was actually clay, so a bit of a hybrid situation. Bottom right, this was a house. There was two family living in there at the time. So also interviewed quite a few people, met a lot of people along this journey, collected samples of render that had a beautiful red render inside. So the image of the hat and the shoes meant to state that these buildings, you need a really good roof. because you don't want the water to get into them, and you really good boots. So the foundations are very important. The foundations are the communication with the soil, so you don't want water to come up. So you want to have a really good foundation and try to isolate the building from the soil. This is very important. So the boot and the hat. So I went around in Italy, so the top left image, trying to chart the regions that had these buildings and different methodologies that were used. And the top right image, I collected then for every building 1 square meter. 1 square meter, I photographed it, and then I drew it up. So basically, I catalogued the size of the bricks, the lengths, the widths, how many bricks were in that square meter, and I sort of all charted them along. So this was the first time that this type of study was ever done. The bottom left, then I drew up a map and I charted them on the map. So at the time there was no Google Earth or anything like that. Talking about probably more than 20 years ago. So it was a lot of hard work getting maps, scanning everything in, going around with the maps on my motorbike, trying to find these sheds, houses. Some of them even have chickens in them now, but they were used for habitation. So, and the bottom right hand side, we have this drawing. This is a drawing done by computer, because heritage and restoration in Italy is generally all done by hand, and it has got certain techniques that need to be done. So need to be, I'll just see if I can zoom in. You can see that a little bit better, but it's a little bit grainy, but it shows all the herringbone, the stones, and different techniques that are used there. So it was the first time challenging the professor trying to use the computer on there. Okay, so Earth is possibly the ultimate green building material. Earth is abundant and inexhaustible natural resource. So how do we meet the challenges of comfortable, safe buildings while reducing the energy used in construction, heating and cooling of buildings, improve the indoor air quality and longevity of the buildings, and reduce toxic waste to landfill? How do we raise the living standards of the poorer people and maintain ours without depleting resources, increased environmental degradation and loss of biodiversity? And how do we build and enjoy our existing lifestyle and reduce our need for fossil fueled energy dramatically and spiraling energy costs? So, of course, Earth can be a fantastic solution for this. Now, in these top images, I did quite some work in Saudi Arabia. It was a complex of around 20 hectares of these earth buildings. So it was a huge city with just ruins. So what we did, the company at the time, we kept most of the skin of these buildings, and inside we inserted some modern museums, and trying to keep, of course, every situation was different, but these were very vast complex, and you can see these holes on the top of the left-hand side building. They call the aeration holes for wind to pass between the buildings. The walls were also up to 60-70 centimeters thick, so that would allow the heat to not penetrate to the other side of the wall. So by the time the sun was lowering at the horizon, the heat would be dispersed back outside. So you got these ventilation holes on the top right image where each house had a different type of shape. It would also be identify sort of the class the family would belong to. So earth building is a renewable technology because the material is simply borrowed from the earth for the life of the building and can be reused and recycled indefinitely as a building material and returned to the earth. The thermal mass of earth can be used to store both warmth and coolth, balancing diurnal fluctuations in temperature in all seasons. Earth building therefore uses basic solar technology to produce the building and maintain comfort. So as you can see in the ruin, we have a ruin, but you can't really see waste because the earth goes back to the earth, and that's the way it should be. So our materials nowadays, we talk a lot about green buildings, but sometimes unfortunately it's just called greenwashing because those materials are not really sustainable. We should keep doing with our research in materials that are really green, really sustainable. So you can see here ventilation holes. You can see also these lines that are on the facades on the top left image. These are called lifts. So the wall would be rammed. It would be pressed in layers of around 400-500 high, pressed in layers until you got to the top. And so you can see these these layers. You can see in the bottom central image some stones, and these are just drums of a column, so they will be stacked on each other, and they'll create. You can see also in that image some stones at the base of the wall, because they will be very important foundations, and to avoid hygroscopic water going back up in the walls. So the foundations are very important. So wind towers, ventilation holes and chimneys, and climatic regionalism. So we want to look back at our vernacular, not at modern city symbols. So local indigenous or traditional building systems often use climate responsive designs and are appropriate in relation to other environmental factors like weather and natural hazards. So in this was in Riyadh, Saudi Arabia. For example, in the center of that city, they built 2 massive skyscrapers, and the heat release, the reflection of the glass was actually melting some cars that were at the bottom of on the road. So unfortunately, they could be located in New York, in Riyadh, or in Sydney. It wouldn't really matter because they have no identity, and it doesn't create a sense of place either. So building with earth, there are many methods. These are just some of the methods. There are as many methods as probably different types of or populations that are on earth, because everybody uses a different method. And you can see here some images on the top left. They're from Carl Earth in California. They build with bags made out of polyester bags or recyclable bags. They get filled with earth, and they get stacked with barbed wire. In this catenary shape. It reminds us a little bit of Gaudi. And this shape, they're very resistant to earthquakes. In fact, they resisted several earthquake periods. You got a person here actually carving out a block as it would be a block of marble. So that's called cutting blocks. We've got churches in Europe. We got earth which gets sprayed on. We've got Rick Joy in Arizona. We've got Shibam, we've got the skyscrapers, we've got Mexico, Africa, and there's also some of these we used for Star Wars. So you got a very old type of habitation. You got the modern technology and all the craft of Star Wars. So the beautiful complex. So from terrestrial architecture, so we will move on now to space architecture. So what does space architecture do? It manages the complex nature of space projects via a multidisciplinary approach. We need collaboration amongst professionals to work towards success. Basic necessities are habitat, greenhouse, power supply, vehicles, environmental life support system, environmental control. So we're going to now try to link the terrestrial architecture to space architecture, and where we want to basically head is the importance of using local materials, which is always the key. One of NASA's priorities is sending humans to Mars to expand rapidly the amount of science that can be accomplished on the planet, and this will bring benefits to humanity and internal collaboration. So going to space, many people think, well, going to space is just a waste of money, but the everything that we use nowadays is coming from space almost. Even if we think about, you know, our devices, our phones, the GPS systems, and all the satellites that are out there for our communication, and all the spin-offs that come from space. Even just talk about the new materials, you know, even Invisalign braces. There's so many materials and spin-offs that come off from space. It's very important. So let's just look for a moment at what is an extreme environment. Extreme environment. So we just broke this down in gravitation, cosmic rays, fine dust, temperature, meteorites. So gravitation and microgravity on orbit. So an orbital situation. On the moon, we've got 1/6 of the gravity. On Mars, we've got 1/3 of gravity. Cosmic rays are very dangerous for humans and equipment, and particularly ionizing radiation. Fine dust are dangerous for humans and equipment because particularly the dust is generally very sharp. Temperature, we've got high thermal gradients that go from 150 to -150 to +120. And meteorites are dangerous for humans and equipment. So there's a whole lot of situations that we need to take in account, and designing for another planet is not something that can be done in isolation. So there's there's a number of professionals that are needed to explore different problems and keep as many problems under control. So let's go through a quick checklist. So we're going to focus on Mars a little bit more on this talk. Otherwise we'll be here for many hours talking about the Mars and the Moon. Actually, my PhD, I'm concentrating more on the Moon at the moment, but there's so many interesting parts of to go through, but we'll go on to Mars. So we've got the positives of day. The day is 24 hours and 37 minutes. Mars appears to be water. Gravity is 3 hg of Earth. The wind is 1% force of Earth's wind, but the sand carried remains very abrasive, and there's also dust storms that can last for weeks. Location is nil electromagnetic noise, perfect for biological and nuclear testing. For the negatives, the pressure is 0.010 atmospheres, so it's 1% of Earth, but has a variation of 30%. Atmosphere is toxic CO2, so we can't just go there and get out of we need to have suits and a pressurized environment. Temperature goes -20 to -153 Celsius. The dust is incredible. So we got from machinery and respiratory issues. Pervasive on the surface of very fine grain. So whatever type of machinery that we will be using would need to be basically machinery that would need to be re-engineered. Anything with pistons and moving parts that will get clogged with dust. It's a little bit like in Saudi Arabia, we had dust coming even inside the fridge. The dust is so fine that it penetrates everywhere, and plus this dust is very sharp, so it breaks down most of Earth equipment. Radiation, so we've got cosmic radiation. Protons are likely to penetrate the atmosphere. Mars' thin atmosphere allows more ultraviolet light to reach the surface compared to Earth, and harsh for humans and environment equipment. Subsurface geology is little is unknown. So what we generally do is we do analogs. So we can have analogs on Earth, which we recreate an environment, trying to study what would happen on Mars. So there's no perfect analog for terrestrial habitats. Planetary, extraterrestrial, orbital, various gravity, polar bases, each has its own limitations. Though they're not completely useless, they're transitional places, are not truly permanent. A different spectrum of tolerances. So what I'm trying to really say is that when we have an analog, say for example, we have a Mars analog on our planet Earth, and we have a mission where we want to stay in complete isolation for 3 months, it's still not completely being able to put on the same level of a real mission, because if, for example, there's a dispute that arises, somebody can easily say, you know what, I had enough, I'm going to get out of this mission, and this has actually happened several times. You also know that you have safety at maybe 20 meters from the base. You can get out of the situation at any moment, but being in isolation, I mean complete isolation, which probably none of us has really experienced, is a complete different thing. So there's no real risk. There's ability to quit at any moment, and the social dynamics are a little bit different. So the spectrum of perceptions and experience is different. The sense of confinement and isolation and physiological dimension is completely different. So what I'm trying to say is these analogs are very important, and we just have to have different types of analogs. There's been analogs also to research architectural spaces and what type of spaces we need. There's been reports on privacy issues, and you know, the walls were too thin, there's not enough light. So there's all these parts of research are interesting and necessary, but they can never compare to the real situation. Mars resources, what has been found in a variety of special regions. Atmospheric gases, 95% is carbon dioxide, and then we go another a range of small percentages of other gases. Solar energy capacity depends on the location and the dust storms. So we need to find the best place to put our base. Metals, there's a huge amount of basalt, like the moon. And then there's magnesium, aluminium, titanium, and a variety of other trace amounts. So the regolith is silicon dioxide, iron oxide. There's near permanent sunlight areas, which are great for power energy generation and storage, and near permanent darkness are great for fluid storage and scientific instruments. And there's a near vacuum. So there was Nader Khalili, an Iranian architect in 1984. He invented this super adobe, which he actually participated in a competition with NASA for a lunar outpost, and he came up with this great idea to fill these bags with lunar dust and create these cocoons, which was a great idea. So when we talk about using materials that are from in situ, we call them ISRU, so in situ resource utilization. So using materials that come from the place. So this comes from, I'm trying to link this with what I showed before about the earth buildings. So that is also in situ resource utilization. I suppose in Italy, for example, it's very easy to see when you go in a place where there's a lot of clay. You will see the whole town built with bricks. When there's an area where there's a lot of limestone, the whole town is built with a stone. So you have this regionalism. You move around and you see materials that are used to build that place up. And that was a little bit different, for example, from Sydney, where you wouldn't see that, and you don't see that in modern cities nowadays. So of course, when we got in situ resources, there's a lot of disciplines that are involved. So we got manipulation, processing the materials, reagent processing, power, manufacturing. Materials that we can use on Mars can be smectite, basalt, silica. So I'll go through then a competition that I won, which was an international architectural competition, and show you some of the materials that are used here. So, and in the right-hand side of the image, you can see the concept of Nader Khalili. This is a mixed combination. So you've got an inflatable inside, so to a certain pressure, and the pressure of the inside is actually way vaster than what's on top. So on planet Earth, these bags would weigh a ton, but in a space environment where the gravity is different, it's just barely, very lightly staying on that pneumatic surface. But of course, there's also issues of the dust, friction between the atmospheric pressurized structure and these bricks that are on top. So there's always things that we need to be worried about. So if we're going to build a Martian outpost, there's ISRU, of course. So we spoke about smectite, basalt, silica, and scientific research. So what do we need to protect? So we have radiation shields. We need a radiation shield because we have ionizing radiation that is penetrating, and we wouldn't be able to, we basically would perish. So because there's no magnetic field, it's 2.5 higher than on the ISS, this radiation. So the terrain, we would want to find something that is flat and smooth. Also on the Apollo missions, when they were landing, they moved slightly because, you know, they were finding boulders everywhere. So you want to land somewhere that's possibly as flat as possible, a natural landscape, which I don't know, there could be a nearby crater, there could be a nearby group of boulders that can protect us from the hazards. And there's been Charles Nevis that has been publishing a lot on contour crafting, so on this 3D printing, which been a lot of studies done on the 3D printing. It's very interesting. 3D printing has to always be done when we do the analogs, for example, in laboratories, showing different type of gravity, because the spouts, for example, of these 3D printings, they constantly get clogged, and also the pressure of the material that comes down has to be have a certain viscosity that it will run through the printing devices without clogging. And so it is not the simplest situation. When they do the animations, it always looks easy, but being there, or actually not being there, making the robots do that, because it will be possibly a robotic mission initially that will be building the structures without having humans do all these risky operations. Something can go wrong. So it needs to be studied, and there's lots of scientific papers that are constantly looking at new ways of doing it, of course. So what are the necessary construction elements? So we would need a number of things. I've just done a very brought it to the nutshell, basically. Communication, so we need internal utility roads, landing pads and access. There's going to be, of course, a lot of dust issue. So where do we land? Do we want the dust to come where the habitations are? So there's a lot of things to think about. Shielding, so we need shielding against radiation, meteorites, exhaust plume protection. So when the craft would be coming down, landing, we would have an enormous amount of dust. So it is called the plume protection. So we could have some sort of crater built around, if you think, some sort of crater built around the landing equipment. So we need blast protection for hangars and equipment maintenance, lighting, 5G, power, ISRU processing plants and inhabitants. So blast protection for all of these. Trenches for infrastructure, burial and foundation. So we don't want to have poles. We want to try to have trenches and bury as many things as we can, but of course in a certain organized order fashion, so that we can then access them for maintenance. Then we'll have a whole area for mining and processing. So mining of regolith for construction elements. So regolith covers the entire surface from meters to tens of meters, formed by weathering processes. So we can have sintering, which is fusing particles together with an enormous amount of heat and pressure, without, of course, melting the materials. Then we can have rammed the material, where, like the rammed earth, you can pack the material, pressure it, or extract minerals from the regolith. So we can extract minerals under certain condition with certain chemicals, under certain heat. We can extract determined type of minerals from this regolith. We can do 3D printing, we just saw. We can have smectite for Subaru Dobby. I actually used the smectite in the competition. I'll show you. Smectite, for example, is a type of clay that is used on Earth, and we don't really use it for the Earth buildings because it varies with humidity. So because we have rain on Earth, it will crack. But it's perfect on Mars because we don't have rain, so it's a perfect material to use. Then we have mining of water from craters in shadow. So consideration, the future buildings would be energy producers and be made by local resources as per the past. So we can see more and more our buildings also on Earth have they might have solar panels, they might have windmills or some sort of device put in the close by river. So we are trying to, we are understanding that we need to produce energy also because our bills are constantly growing. So what I believe is these future buildings on planet Earth, but wherever there will be on another planet, there will be energy producers. They will be producing, it will be just normal that these buildings will is not possible to be exporting energy from Earth. We'll be capturing energy from the sun. We'll be extracting energy, but we will be independent. So it's very important. So here we're going to just go through the health considerations, the so-called stresses. The stresses can create a degraded performance, and the degraded performance can create a hazard. So the stresses are something that are not physical, but are caused also by physical situations. So let's just go through them for a moment. So if we're going for traveling to Mars, we can think about that. We will be traveling in darkness for several months. I believe it will take at least 6 months with a micro society and interpersonal challenges. So think about being in this cylinder for months with the same group of people. So it might be okay for a first few weeks, but then there will be interpersonal challenges and cultural challenges amongst the group. Extended stay, so we're forced interaction with a small multicultural group. There's no separation between work and social, so it creates a lot of friction. The real two-way communication currently not available, so there's huge delays in communication. Confinement in extremely small spaces, so we're talking about very reduced privacy. So you might have the kitchen near the bathroom, or the bathroom near the bedroom, and the bedroom is not a bedroom, it's just a bed. So, you know, in the bed it might be bunker bed. So, you know, situation, the space is very confined. There's no emergency evacuation. So something happens like serious illness, danger, suicide, death, violence, family separation. So why am I talking about emergency evacuation? Because there could be a situation that is not created on Mars. There could be a situation that is created from a family friend on Earth. Let's say, for example, there could be a family friend that feels ill and is very close to us. So that creates to us that is on Mars in our mission, we could be severely depressed all of a sudden and want to go back to planet Earth. So there's no emergency situation, evacuation, we can't just go back. Social isolation, so there's no family life, the disconnection from the real world, the crew norms and agency policies. So of course the crew gets you know, has to work on gets trained on what the policies are, and also every agency has different types of policies, so there might be, you know, some friction there between the crew. Crowded feeling, loneliness and separation, so limited availability, hygiene and sleep. So it's not meant to be a depressive list, but it's meant to just go through the health considerations. You know, what are the stresses? So there's an amount of stresses there. What are the necessary space architecture elements? So nice to have elements becomes vital with longer mission duration. So the longer we are out there, then the more necessary these are. So access. So we want multiple access to important areas for functional and safety reasons. Egress, dual, remotely separated exits from a given room. So we want to have 2 egresses from every room. Circulation loop means of translating around a base or habitat. So we want to be able to get around the habitat and not be isolated, have a group of habitats. Public space, common living, gathering, circulation. So public spaces often will be spaces that normally on planet Earth will be external, but in Mars there will be internal public spaces. So sort of a hybrid situation. We'll have an internal park. Work lab areas for research, and we'll have so many different type of researchers. It's inevitable. Plant area, so we'll have agricultural research, and we'll also have plants to sustain and produce food. Life support areas will be essential. Surface mobility, travel safely on the surface, or we'll have vehicles to move around, and robotics, so they'll be autonomous and teleoperated. So a lot of these very dangerous processes will be done by robotics. There'll be no point in exposing humans to processes that could be done by robots. I will slowly go now into presenting the competition. So I won an international competition. It was for basically designing a habitat for 9 astronauts to live on Mars for 2 years. So that was from Mars City Design. It was sponsored by NASA, ESA, National Geographic, and a whole lot of other companies. And I did a lot of research on food, because it was in the competition laid out that we had to think about the food and how we had to select a certain type of cultivations and put them through a software which was called the Eden ISS project. Basically, this software would go through all the different cultivations and then be able to tell us if the 9 astronauts will be living, or if at the end they would run out of food. So it was very important to study this. This Eden ISS project is basically located in a very extreme environment. So you can see it's basically like a shipping container, and inside it has all these plants. These plants are using the LED lights to control different type of quantity of light that goes to different types of plants, and they have the nutrients that are separated. So how big is the greenhouse? So we have 500 square meter cultivation. It can serve 4 crew approximately. What are the plants that eat, and what are the post-harvesting systems? So these plants, the fruits would generally, for example, not in this system, but in the future, they'll get harvested by artificial intelligence, which will be automatically be seeing which is the red tomato compared to the green tomato. So all these systems that will be automized. So what requirements do we need? So the whole settlement, we have to think about it as a living organism, independent from herb, able to ingest, digest and excrete, ability to excrete air, soil and expand, and survival via life support systems, air and water. So I think now I'll just go through the competition. So this will go 3 minutes. It's a video, and I will not be talking for that amount of time. Here we go.
In the proximity of the ancient delta, AI robots will install battery storage containers, nuclear energy generators, and solar farms. Following this, they will create bricks from extracted smectite of the delta and use extracted basalt fibers and bioplastic for 3D printing. AI will be digging trenches and printing foundations for the algae pools of the Green Powerhouse, a system invented by Michael Smith. After installing the photosynthetic collector core, compressed bricks will be locked together to form the walls, and the whole structure will be closed with 3D printing of the Nubian vaults. Extracted silica will be shaped into glazing to close each end of the vaults. The Green Powerhouse mimics natural biological processes. It is an integration of 3 subcomponents: photobioreactors, anaerobic bioreactors, and organic carbon engines that work together to convert biowaste into energy and soil amendments. The photobioreactors utilize a light source to cultivate algae. The anaerobic bioreactors will convert algal biomass into methane, hydrogen, and organic fertilizer. The organic carbon engine is a biomass-powered device that generates biochar, a product that locks in carbon and generates soil at 1000 degrees Fahrenheit in absence of oxygen. Byproducts will include electrical power, high-grade organic fertilizers, and soil amendments. Once the Green Powerhouse is built, the laydown of the bricks will proceed to create arms of a secondary structure, hosting and protecting greenhouse cylinders and habitat modules. The arms will be capped with 3D printed Nubian vaults, with glazing, permitting natural light penetration. The plant's main source of light will be from LEDs alimented from solar collectors. The greenhouse cylinders will provide bio-waste to the Green Powerhouse, and the Green Powerhouse will supply biochar in return. Sprout is the system that produces no waste in a perfect closed circle. Once the shielding walls and roof structures are completed, the pressurized greenhouse cylinders will be opened and placed. Seeds will sprout and crops will grow and flourish while earthlings approach. At their arrival, waste from crops will be moved into the Green Powerhouse and dealt with immediately, creating the power that will sustain life on planet Mars. With the expansion, a seed vault and insect processing area will be added. Sprout introduces a self-sustaining, self-managing ecosystem that can be utilized for the year-round production of organic food in virtually any climate, with both Earth and Mars applications.
Okay, thanks for patience on that. So that was the competition of Mars City design. I'll just go through now to finish off the talk. I'll just go through some of these sheets that I prepared for the competition, just to show you a little bit of what was involved. So basically I got inspiration from the snowflake, as you can see, a snowflake which is a fractal. I did a lot of study on, I am currently doing a lot of study also on the layout of the habitats and which one is the best layout. The staggered one appears to be the best, and after just before the radial. So the radial, as you can see, it allows these communication roads to be not intersect, so to be able to go radially, you'll be able to have many of these snowflakes and put them one against each other. So what I did, as you can see on the left-hand side, there's an image from a satellite, a remote sensing. You can see the different colors. So this competition is located in Jezero crater on Mars, and the Jezero crater, there is apparently there's a presence of smectite, as you can see in the picture, this blue colored clay, and the smectite is present also on Earth. But the great thing about the smectite is that it does not expand or contract on Mars, because we do not have the humidity for that to happen. So collecting that smectite and compressing it into bricks is a fantastic thing that can be done. So that links again, learning from Earth, ISRU, and applying it to another planet. Also learning from our history. So we all know about the Nubian vaults. The Nubian vaults, they get done on planet Earth with these bricks, and the bricks, you can see if we had a normal vault, Roman vault, we would need a scaffolding system of wood underneath to hold up the whole system. But here we just lay everything at 40 degrees and we can keep on building with bricks. But in this case, a modern technique would be using this with 3D printing, so that we can make the robot basically do it with basalt fibers and have then the bricks against it. So the whole idea is not to live straight away inside this structure, but to have a unpressurized structure, which is this, and then to have a pressurized structure inside these. So these are basically shielding us against all the meteorites and the radiation, ionotic radiation, cosmic rays. So as you can see here in the bottom, we have these structures that are shielding us, 3D printed on top, and then inside we have these ISS cylinders. Basically, these cylinders that get sent by Earth, and they get expanded, as you can see from the video, and they get slotted inside, and then they the seeds sprout basically. So here I use a software called CMOC, which was required by the competition, and put in different types of cultivation. So peanut, rice, lettuce, tomato, spinach, radish, snap bean, pea, and then we had areas for habitation. Areas for habitation are these ones on the side initially. This is just for the 9 people. And then it gets expanded to 22 people. And in this one here, I had then whole insect area and seed vault. Insect area, very important, not only for the plants for the pollination, but also for a source of protein. And also, as you can see, for example, there is no wheat here. The wheat would take months to get to maturity. We use up a lot of water, and the software told us that it was not a good way to create flour, so the flour was produced in a different way. So the selected plants then gave us a favorable response. So really hard to satisfy the software, and with the food, inhabitants, the duration of the mission, the amount of batteries, and the amount of CO2 scrubbing. So we'll go through all the graphs, but I don't want to bore you with all of this. So you can see this is a setting with 154 people, so still the fractal continues, and then we have this sort of hexagon. Can be also seen a bit of as a beehive. So at the center of each of these is a green powerhouse. So each of these systems is totally independent from the other one, and that is the great thing, that all the waste that is produced by all these plants gets inserted inside the green powerhouse, and that creates biochar, creates energy, and then powers the whole system. You can see the location. So this is the purple area where the smectite is found, and you can see the delta and the crater and the Jezero area, solar farm around it. And then there was another crater where there was the nuclear generators, and they will be hosted later. The initial nuclear generators were a little bit closer. So this goes in a lot more detail. You can see all the non-pressurized compartments, the purple, and then the pressurized compartments, and the ability to go from one area to the others with all these ISS. So the ISS, the one that I showed you with the shipping containers, that then there've been a lot of studies that have been made for, you know, how do we make this into a situation where we could study these plants on another planet. So these idea came along, and we have the central area with the algal raceways and the photosynthetic core at the center. So of course, this green powerhouse, this was invented by Michael Smith. There is a movie that you can see for free on the web. It's called The Need to Grow. And Michael Smith, he goes through all this green powerhouse and how he calls it the dragon. This big machine is being able to create humus, biochar, similar. They're different, but it's basically a soil that is able to be used. And how fantastic this system is, because it makes soil from a period of decades into a matter of days. So the whole process is sped up incredibly. So I have these solar collectors, these big yellow devices that are basically collecting the sun and then bringing it back to the plants in form of LED lights. So these Nubian volts are 3D printed on top, covering all the machinery of the green powerhouse. Some of these pressurized cylinders also have skylights on top, so they're able to get some sunlight inside. So yes, the silica that's in situ, that will be melted and formed into these panels that will be able to shield, allow some of the light inside, and then the rest of the light will be gained by the LED plants. So there's space around the cylinders for maintenance and being able to go underneath and around these cylinders. And so here we have these rovers, and these rovers, my idea would be to have a few rovers, but the rovers will be able to have a number of mechanical arms. So they'll be able to have a scissor hoist, they'll be able to have cameras, being able to have attachments for the 3D printing, because if we sent one rover for every function, we would have a situation where we would have a breakdown of one rover, and then the whole construction would have to halt. Well, every rover will have to be able to do a several amount of operations so that the construction can speed up. And then when it's time for 3D printing of the roofs, then all the machinery, all the rovers start 3D printing, so the whole thing can go up in a quicker fashion. So here we have some 3Ds and some sectional elevations of the whole complex with the plants. So the plants, the whole cylinders would be shipped from Earth and pre-planted initially with seeds, and then robotically they will be opened up, the cylinders that will be sprouting. And so when the astronauts will be coming, they will automatically or already be finding the whole harvest ready to be used. And so here we're just showing in the bottom right image how this application is for Earth. It's for Mars, but it's also for Earth. And actually, because we're having on Earth all these problems, and agriculture is actually creating so many problems with, and we're using more and more pesticides to combat, weeds and bugs. Actually, the bugs and the weeds, they're getting bigger and harder to combat. So it's a vicious circle. How many products and chemicals can we put in the soil? So we want to create some sort of super seed on Mars, where these plants will be resisting radiation and resisting a very harsh environment, and bring those seeds back to Earth, and possibly they will be much more resistant. So that will be also an idea. So I hope you enjoyed this. I think I don't want to go any more than that, and so I want to say grazie, thank you for your attention, and I'll leave it back to you, Peter.
Grazie, Giuseppe. On behalf of the committee and members of the London Heathrow branch of the Royal Aeronautical Society, I must thank you for giving up your valuable time. Let me move on to some questions. I'm going to ask you some questions that I've thought of. Personally, and I don't know how other people view you, I'm an aeroplane engineer. It really is interesting to see such a different lecture. The parallels of sort of medieval architecture, old architecture. It's not necessarily medieval, it's still around, as you say, in the poorer parts of the world. The parallels were quite interesting to see, and the health considerations, the stresses as you call them, yeah, I can see kind of where it all fits together. As I say, I'm a bit of an engineer, so I've seen a lot of what I call creatives in my design organisations that I've managed, and your mind is very akin to them, with a thought of this and that and the other, and the links have become quite diverse. Anyway, so you're talking about mud bricks. I can see that. I can see how you'd use them. What about the water? Are you drilling for water deep in Mars? Are you going to photo chemically produce the water? How will the water come together?
With the remote sensing, they've been demonstrated that on Mars there is actually a lot of water. There are craters that are full of well, what looks like ice. Until we actually go there, there is always a question mark. Like, is that actually ice? It appears exactly like what we have on Earth, but until we go there, we wouldn't know for sure.
I guess the answer is until we find out if there is water, and what we think's water, we don't know. So let me leave that one. Looking again at the settlements that you've looked at during your studies of similar settlements on Earth, I think of Italy, I think of Sardinia, I think of Nuraghi. Yeah, am I using the right word, Nuraghi? Yeah. I guess there you've got the same sort of beehive arrangement where you've got these cellular structures that are get together. It's interesting how going back, I guess, again, Nuraghi, answer me again, you're a good Italian there. Nuraghi are I'm not sure whether they're pre-metal or post-stone. Where do Nuraghi sit in timescale development?
They'll be medieval. You're talking about the one in Sardinia, right?
I've seen them all over the Middle East. I've seen them in Cyprus. I've seen Hill Nuraghi in Sardinia. I think they're older. I think they date back to pre-Metal Age. I think they're post-Stone Age, but they're just pre-M Age.
Probably looking around 7 to 1,000 years before Christ. Those that we have in Italy.
Sorry, I paused. I muted myself. Yeah, I see your structures kind of reflecting these Nuraghi type structures. I see how the mud bricks come in. I see how the stones, as you call them, are used as foundations and bases. Yeah, I can see where that's all coming from. I'm looking at that. Was it Khaliti, the Iranian? His work.
Yeah, another Khalidi, yes.
Yeah, if you look at his pictures, they're very like the kind of structures that you've demonstrated. They're very like the structures that I've seen all over the world. I think that's great. I really do. I can see where your mind is coming from. Going on, dust. I may not be a great astronautics enthusiast, but I have followed. I am a helicopter enthusiast, and I followed Ingenuity, the Mars helicopter. You were talking about dust. Dust has been a killer, I read recently, to Ingenuity. Tell me how dust is going to affect the collection of solar energy.
Well, dust, of course, will create a layer on the solar panels, so it's inevitable we'll need some sort of device that will constantly be cleaning the solar panels, and that is not really a good idea just to rely on the solar panels. So therefore, with the dust storms, they could be covered for entire weeks. So we want to have solar panels, but we just I suppose as a backup, we need several sources of energy. So we need solar panels, and then we need also the nuclear energy, because that is really the reliable source of energy that we can have, and solar panel and anything else that we can find as backups.
Okay, we were talking about cosmic radiation. Follow your comments on dust. The answer to the question really would have been, I guess, yeah, dust means that we're going to use solar panels in a secondary role. Yeah, totally understand. Thanks. Cosmic radiation. Let's go on. Opportunity. Both opportunity and ingenuity as machines. They don't seem to have been too badly affected in the months they've been sitting on Mars. They're still operating. They don't seem to have been too badly damaged. I'm not sure how well screened they are from cosmic radiation.
You're talking about the rovers, Peter?
Yeah, the Opportunity's the rover, Ingenuity's the helicopter. I guess they're both machines that have kept going despite being bombarded by cosmic radiation.
Yeah, this is probably an engineering question to see how that affects all the technology, but they'll probably have some sort of shield, but I doubt it would affect it like it will affect humans. So yeah, it's probably something the engineers are looking after.
Yeah, my wife would agree with you. She's sort of biological, medical background, and she would say, well, these machines, they're hardy things. Humans aren't. Yeah, I understand where you're coming from. Yeah. What's the limiter, do you think? Is it the buildings or the people for these settlements on Mars?
Oh, I think it's well, at the moment it's probably the buildings, because there's been a lot of studies, but we still haven't come up to a real solution. What methodology are we going to use? And each methodology seems to have quite a number of limitations, and despite talk that we're going to go there in a few years, there still is not really a solution as to what system we're going to use, because all the analogs and digital twins that we're doing are giving us certain results, but there's not one ideal material that we have found. So there's a lot of studies that are happening at the moment, but no, there hasn't been one that's definitely come up as, okay, we're going to use this material. A lot of those operations, they can be done remotely, and they could be done even, operating from Earth. It could be done operating from the moon or from orbit. So I suppose for the moment, the limitation is the habitat is the first thing to think about.
I've got a question from Uma. Hi, since Mars' atmosphere is 1% of Earth, water would rapidly evaporate, I believe. Hence, during the construction of brick structures, I suppose there will be a need for lots of water. So could you please elaborate on the construction process?
Yes, these bricks that I'm going to use, yes, I didn't get into too much of the percentage of water, but what I'm going to use is a technique called compressed earth blocks, CEB. It's called in earth building. Basically, the soil gets put into a machine and gets compressed, and it creates a block. So the compressed earth block compresses the material at such a pressure that it will create a block in absence of water. And not only I will do that, I will then process it with microwaves. So I'm not putting it simply baking it, as in creating a clay brick or a brick, I will be using a microwave, so it will be thoroughly basically fired. So the idea was not to rely on the water at all, but have a compressed earth block. Compressed earth block will be a compressed mud block. Yeah, basically. Compressed Mars block.
So I guess you're talking about compression rather than mud. So you used the word sintering earlier, a sintered block rather than a mud molded block.
Yes, I'm not using sintering though. I'm just purely compressing the material in a form at high pressure without using heat. Yes.
Yeah, I meant it that way. I understood.
Oh, sorry.
Yeah. That's okay. Yeah, that. I think that's answered that question. So I'll move on. Richard has asked a question here. You mentioned small nuclear power units to start the whole process. Will there be an ongoing requirement for this? Yes, I guess you've half answered that one. Talk to us about the nuclear power plants. How are they getting there? How are they being replenished? How will that work? What's your view?
Yes, they'll definitely be sent together initially. It's one of the first things that need to be sent. I mean, even the robots, the rovers, anything that will be there, they will all need power. So power is the first thing. It's probably one of the first elements that needs to be placed, positioned, and worked upon. I was thinking initially possibly a smaller operational unit could be closer to the base, and then as the base becomes bigger and bigger, have it further away for safety reasons. It's purely because at the beginning you don't want to have to travel 20 kilometers or 50 kilometers to maintain the nuclear energy. If there is some problem, you want to be able to access it fairly quickly, and also you'll be having a limited amount of energy, limited amount of resources, so you don't want to be going backwards and forwards too much in the base. So I would have initially a smaller nuclear power plant, and then have a bigger one as everything evolves and becomes bigger in size.
Okay, I understood the answer. Hania, our friend, our common friend, has asked the question, what are your views on using inflatable structures on Mars?
There's a lot of studies on inflatables. To be honest, I'm not a big fan because I'm worried about the particles that are released from the plastic, and with all these radiations and a lot of radiation. I mean, they're still studying these plastics, and there's lots of different types of plastics that can be used. But I'm worried about over time, how much of these particles actually will be released by these materials. So they all look really great, but I've tried to steer away from them as much as possible, although I think there would also be some sort of hybrid situation. We would have a shielding structure, and then inside there will have to be some sort of plastic or inflatable structure. So we just have to continue doing our studies and have a lot of laboratory studies on so reproduce that environment in a lab and be able to try to replicate as much as possible a Mars situation, and see what would be the breakdown of that material, and not only in a matter of days but also in a matter of years. We don't want to find ourselves that material is breaking up and delaminating, because it could be a material made out of several layers, and it's delaminating due to the radiation. So yeah, it has to. I suppose we need to keep on studying the materials. So there's a long way to go still.
Yeah, you're really making me think outside my comfort box. Yeah, I guess that breakdown's a double-edged sword. You could have the breakdown internally, thereby bringing quite dangerous plastic damage to the humans inside, because it would break down equally on the inside and the outside of the building. So you'd be polluting your inside environment. But as well as that, you've got a planet that at the moment is fairly free of the kind of pollutants we have a lot of on Earth. So I guess you don't want it going outside the bubble either. You don't want the outsides of the building polluting the planet itself, do you?
Yeah, it's a very good point as well. We don't want to create the same problems that we've already done on Earth. And also thinking about sustainability, you want to have a material that's completely sustainable, hence utilizing the regolith for what you have there will just break down like the Earth buildings and go back into the environment. You want, if we use some sort of plastic, be able to be bioplastic, maybe extracted from the plants. Some definitely would have to be a sustainable product.
Yeah, I guess again it was that comment you made about return to the Earth. You really, if you're using Martian resource, it's all very well it breaking down and returning to Mars, but if we take plastics or even manufacture plastics locally, we're creating a new problem. Yeah, you're making me think outside my box. Thank you. It's great listening to you, making me think. Thanks. I'm an aeroplane engineer, not an environmental engineer. I should be nowadays, but I'm not. Rayan has asked me a question. In situ resources, including Martian soil, basalt and Martian concrete, are among the most feasible future construction materials on Mars. Are we planning to use other materials in future for our experiments? 2 people have backed that one and I've liked that one, so there's 3 people asking that question.
Yes, there's a lot of materials. I think you can think about biomaterials, so you can think about growing structures. So that's something that I'm actually getting a lot into. So it's not only biomimicry, so getting inspiration from natural structures or like plants or leaves and living cells, but being able to actually create structures. And you can think about structures like grown from mycelium, for example. So that's something that is very interesting. And it's taking a big step here also on Earth. So a lot of materials, polystyrene, will be completely substituted shortly by mycelium in the packaging. There's a lot of studies that have been made also in Venice, for example, how to try to hold up the city, how to grow structures underneath. Materials like secrete, for example, which is creating a current through a material and positioning in a salty water. But of course, there's a lot of that, for example, material cannot be applied on a Mars situation. So, yeah, growing materials and thinking out of the box, thinking how can we do things differently rather than just making things in the way that we do on Earth.
Yeah, I'm going to shoot you some bullets at that one a bit. We are taking this vegetable matter to Mars. Mycelium, we have problems with mycelium on Earth. Are we taking, it's the same question as plastics, are we taking pollutants to Mars to pollute Mars with?
Mycelium, so mycelium is basically the rooting system of mushrooms. So
yeah, we have problems with those on Earth. We have asthmas and all sorts caused by them on Earth, and I guess they're pollutants in their own right to our biological people machines.
So yes, I suppose there will have to be studies done on that as well. And mycelium, eventually we wouldn't have live mycelium. We would have to bring it to a point with the robots. For example, they dehydrate it and they contain it. It's got a a foam, a layer on it, which will beat definitely towards the inhabitants so that it doesn't release spores, but it's definitely going to be killed mycelium, so it won't have the fruiting body of the mushroom. It wouldn't be really, but of course that's why we have scientists keep on studying these materials and the positives and the negatives. Yes.
Okay, thanks. You thought of that one. I knew you'd have answers to all these questions. You're a man there with all the answers. Another one. Go on, hang on.
No, I'm actually studying that material quite deeply nowadays, so I'm really interested in it.
You are the expert. I was right. Question from Uma. You mentioned the cycle of pesticides and simultaneously pests becoming immune is a threat to agriculture as it's harming the soil. How serious is this matter in your environment? Is there a potential for global food crisis related to this?
Yes, there's a couple of scientific papers. There's actually a few more than that. They were reporting about some studies done also by National Geographic. There's only 60 years of, this was in the US, 60 years of arable land left because our agriculture is quite destructive in the way that it depletes the soil. What we are doing, we are constantly planting new plants on the soil, and the soil doesn't have time to regenerate, because normally what would happen is that you would have the forest and the leaves and branches falling down, they will decompose and they'll create humus, and then they'll have insects, and you have a whole system where the soil replenishes and it has time to just re-energize. It's a bit like for us going to bed and sleeping and re-energizing, but what we're doing, we are actually taking away all the energy from the soil, and the soil unfortunately doesn't have a way to replenish it. So what we do, then we put all these fertilizers in it, because it's basically it doesn't have any of its own left, and so it is quite a serious matter. In fact, that's why there's a lot of study also on hydroponics and vertical farming, so we can have on the same, I don't know, 500 square meters of soil, we could have a vertical farm and have multiple layers of fields. So we could have that. We could have 10 times for the same amount of soil. We could have 10 times the amount of produce. So we have this all under a structure. And that's probably the way it's going to go. So have in the city have have skyscrapers that are actually not inhabited, but skyscrapers that are full of food. So have a vertical farm inside the city. That way we could produce food for the inhabitants, and we don't need to travel backwards and forwards and create even more pollution. So there's a lot of things that need to be thought through. The great thing also with vertical farming is that we don't need to we have the plant with the root system, and if we don't sell it that day, we can just keep it there. We don't need to actually harvest it and cut it from the roots. And what happens in agriculture today, we cut all these plants, we bring it to the supermarket. By the time it comes to the supermarket and then it goes to the actual consumer, there can be days and days that pass. So that food doesn't have a lot of nutrients in it anymore. So yeah, it's a big worry because it's only 60 years in their prediction. So as many animals, for example, referring back to Australia, like the kangaroo, the koala, the platypus, they're going to disappear in 20 years. That's in our lifetime. So the same with soil, we don't know what will happen, and create a big problem for the world. Yes, if we don't think about it in time.
Yeah, that's something that we engineers have to think about as well. Let me move on. I'm going to ask you a question. It's obvious we can't get to Mars today. We're getting close to being able to go, but as someone in your discipline, what would you like to drive my discipline, the engineers and the astronautical engineers? What would you like us to drive to get us to Mars more quickly so that your experiments can begin?
Oh dear. There's so many things. I suppose that goes through the whole talk. I mean, even my habitation, my structure is not meant to be by no means definitive, and it's just meant to be a little contribution to the subject, and I am well aware that it's not complete and that it's got a lot of it would be lacking a lot of aspects, but there's just so many studies that need to be done in every field. I suppose I think one of the things that I would focus on would be the travel to Mars. If we could somehow half that from 6-7 months to fewer months, I think that would be a greater thing. I'm just thinking about being completely so isolated and having a situation of emergency, of being able to return. I think being able to transport goods backwards and forwards, and I think that travel is something that that will need to be worked on quite heavily. Yes, I would probably focus on that in the first thing that comes to mind.
Okay, so your driver is get me to Mars quickly. That's quickly in two ways, very soon, and also once we've got the transportation, to make that transport very quick and it's moving, in meters per second through space. Yeah, I like that.
I don't want to give you too much work, Peter.
Well, in my time, I'm retired, but my successors will have to think about moving quickly through space. Okay. While I could keep asking you questions forever, I'm looking at the time. It's 7:30 our time, 8:30 your time. I think that's when we're scheduled finishing. So if that's okay with you, Giuseppe, I'd like to round us off now. Are you happy with that?
Oh, thanks so much. It was really great. Really enjoyed it, and really active audience as well.
Yeah, I thought there were some good questions there. So, on behalf of the committee and members of the Heathrow branch of the Royal Aeronautical Society, Giuseppe, I've got to thank you for giving up your very valuable time in order to tell us all about the possibility of settlements on Mars. I was really interested. Grazie mille. I offer our best wishes to both yourself and your family for good health and for continued good luck and success. I'd also like to thank Hania Modahin, our very active committee member, for so kindly arranging for Giuseppe to be with us this evening, and for William, our Honorary Secretary, for undertaking the administration and IT wizardry which made this lecture possible. With my problems getting on tonight, I can only thank him for his IT wizardry as well. I would wish to thank all of our members, guests and friends of the branch for attending this evening's lecture. I hope that you have enjoyed it and have all learned as much as I have. Now, on to a short branch notice. The next event season will run from September, when we hope that the branch can return to the old normality. We hope that the lectures will return to a face-to-face format in the BA Waterside Lecture Theatre. Into the future, we have developed the additional capability now to run live lectures as webinars. This is something we may want to continue. So watch out for us publishing a lecture programme in the late summer and a calling notice from William in September as an email on our branch events page, in the main society's web pages, and in our social media pages. Finally, I look forward to seeing you all again face to face at Waterside very soon. I wish you all good health and a successful remainder of 2022. Again, grazie mille, Giuseppe.